Hi, this is Somaiah, working as assistant professor in the Department of Mechanical Engineering. Today, I'm going to discuss the momentum equation and its applications. So, in the previous classes, we have discussed the various energy equations, also continuity equation, and here the momentum equation importance is these previous the continuity equation and energy equations, these are not sufficient enough to solve complex fluid flow problems. In order to solve these problems, we need to understand the momentum equation or impulse momentum principle, and so that we will be solving so many complex fluid flow problems. So here, the basically what do you mean by momentum equation? The impulse momentum equation is also known as the momentum equation. Simply, we can call it as momentum equation. And this is nothing but the net force acting on the fluid mass is equals to rate of change of momentum. This is simply the rate of change of momentum is equals to the net force acting on the fluid mass is known as the momentum equation or momentum principle. So these equations are often used in conjunction with the energy and the continuity equations in order to obtain the solutions of the problems of fluid flow which can't be solved simply by applying the continuity and the energy equations. So it is based on the law of conservation of momentum or on the momentum principle, which states that the force net force acting on the fluid mass is equal to rate of change of momentum. So in other words, the principle is a modified form of Newton's second law of motion. So it states that the net force again this is equals to rate of change of momentum, or nothing but it's equals to F equals to ma. So what Newton's second law states that is F equals to ma. So here, as per Newton's second law, the net force is F, and the m is the mass of fluid, and A is acceleration. So here the A can be written dv by dt. That is nothing but rate of change of velocity is acceleration, and if you substitute A in F equal to ma, this can be written as F equals to m into dv by dt. So otherwise we can write F equals to dmv by dt. So here this dmv by dt is rate of change of momentum. This is nothing but rate of change of momentum. Rate of change of momentum. So this is equals to net force. So that is denoted by F. So entirely what you can call this F equals to dmv by dt is nothing but momentum principle. Entirely you can call it as F equals to dm by dt, and it's also known as momentum principle. So in other terms we can write F equals to dm by dt also can be written as F dt is equals to dmv. So where it indicates the net resultant force is F acting on a fluid mass m for a period of time dt. Okay, so then it causes a rate of change of momentum is dmv. So this is F dt. You can rewrite the momentum equation as F dt equals to dmv. So where the impulse of force acting on fluid mass causes a rate of change of momentum. So this is known as impulse momentum equation. So now we will see the various applications of momentum equation. So in impulse momentum equation, basically we will come across of a lot of problems like pipe bend, propeller, and jet propulsion, etc. In various cases, its net resultant force acting on the fluid, so that can be calculated by you applying the impulse momentum equation. So in order to apply and solve the complex problems of fluid flow, we have to consider a control value of any fluid passage. So similar to this fluid flow, here two different sections are considered in a varying pipe dia of cross section. At one where the velocity is acting v1 and area is a1 and angle of flow along with about x is theta 1. Similarly, theta 2 is angle at section 2. So where the velocity, pressure and various forces are acting. So here 1 to 2 is a control value. So here we have to consider for in order to find out the resultant force acting on a pipe bend or resultant force acting on a fluid mass, so that we can be calculating by assuming a particular control value. So here the curved portion, is a section 1 dash 1 dash. This is 1 1. The section is a straight line, but here it became it is a curved one. Here another one at 2 2. Again, it is deformed to 2 dash 2 dash. This is due to the non-uniform velocity of a fluid flow. So if the velocity is varying with respect to time, so in such cases the shape it will be deformed like this. So by the primary thing is we have to consider a particular control value, and we can apply this momentum equation or impulse momentum equation for steady flow, for unsteady flow also. So we will and we can consider the pipe of uniform diameter and non-uniform diameter. So etc. For various cases we can apply the impulse momentum equation, and along with energy equations, continuity equation, and finally we will find out the net resultant force acting, and some other unknown parameters like pressure, velocity also can be calculated in magnitude and direction. So and you can calculate the angle about which the flow is taking place. So these are the some of the applications, and since the impulse momentum equation relates the resultant external forces on a chosen free body of a fluid or control value in a flow passage to the change of momentum flux, where momentum flux is nothing but mass into velocity, the mass times velocity. At the two ends, it is especially valuable in solving those problems in fluid mechanics in which detailed information about the flow process within the control value may be either not available or rather difficult to evaluate. So in such cases, in where the complex situations are there, where the fluid flow in that fluid flow we need to calculate unknown parameters in a variety of different complex situations. In such cases we can adapt along with the energy equations, continuity equation, and we will apply the impulse momentum equation so that these difficult problems can be solved. So that is the necessity of the momentum equation in order to solve the complex problems. Thus, in order to apply the impulse momentum equation, a control value is first chosen, which includes the portion of a flow passage which is to be studied. So, in this diagram, we can see the control value 1 to 1 1 and 2 2. In between these two sections will consider this is a control value to be studied, the various parameters and the various forces acting on that control value, and at that control value at inlet at section 1 what are the directions of flow, and what are the forces acting, and similarly at exit of control value also what are the parameters in which direction and by what magnitude they are acting, they will be studied, and some unknown parameters can be evaluated by the application of impulse momentum equation. So the boundaries of the control value are usually extended up to such an extent that its end sections lie in the region of uniform flow. So where uniform flow is dv by dt is equals to 0. It should not vary, velocity should not vary with respect to the time. So such type of flow is a uniform flow. In some cases it can be applied to non-uniform flow also. So all the external forces acting on this control value are then considered, and the momentum equations in the corresponding directions of the reference are applied to evaluate unknown quantities. So like pressure, or maybe velocity, or maybe direction, their magnitudes, then the resulted forces. These are some of the unknown parameters. In general, the impulse momentum equation is used to determine the resultant forces exerted on the boundaries of a flow passage by a stream of flowing fluid as the flow changes its direction or the magnitude, or both. So, in both the magnitude and direction, these parameters can be calculated. The problems of this type include the pipe bend. The first, majorly, it can be applied on a pipe bend. So the pipe bend will be in different diameters and different orientations. Okay. So for such type of pipe bend, we can apply. We can consider the particular control value. So we can consider particular control value. So in this region, we'll apply the impulse momentum equation to find out the various forces, and various other unknown parameters can be calculated. So before that, we have to assume the first thing is we have to consider a particular control value. So furthermore, it can be applied in propellers, also in stationary vanes, impact of jet on vanes or plates. So it may be stationary, or it may be fixed. It may be stationary, or it may be moving. One in the cases also we can use, we can apply this impulse momentum equation. So furthermore, the impulse momentum equation may also be applied to solve the problems of non-uniform flow also. So in which an abrupt change of a flow section occurs. So where the velocity abruptly changes from section to section with respect to the time. Any time, at every time, it may be changing for every second. The problems of this type include sudden enlargement in pipes, hydraulic jump in open channels, etc. The sudden enlargement, the nothing but a flow passage. Initially, it may be with a small d, so immediately it may be extended, or its area of cross section will be doubled or increased to capital D. So therefore, in sudden enlargement or in the sudden contract, if you allow the flow in this reverse direction, it becomes a sudden contraction. So, and if you allow the flow in this direction, this becomes a sudden enlargement of pipes. In such sections, we can find out the forces. So the application, it's one of the application is jet propulsion, or reaction of jet. So here we can see what is happening. So there is a liquid in this tank. There is a small orifice at the bottom. If you allow the liquid to flow through this orifice, then it moves with a particular velocity. But before, at the time of leaving, due to this narrow section, there will be a force in forward direction. But as according to Newton's third law, for every action there will be equal and opposite reaction. Equal and opposite, therefore it applies a back kick. Otherwise, backward force will be generated. So that is that will be used in jet propulsion, or this is called as a reaction of jet. So its action will be in the forward direction with particular force, but it applies a back kick, otherwise back force, that is with its equivalent opposite force, equivalent opposite force in another direction. So this is another application of impulse momentum, and the force exerted by the jet on the source from which the reaction of the jet, and is therefore equal in magnitude but opposite in direction of the jet. Further, if the source issuing the jet is free to move, it will start moving in the direction opposite to that of a jet. If the jet is moving in the direction, reaction forces will be in the opposite direction. So thus the reaction of a jet can be utilized for the propulsion of various bodies. So the principle of jet propulsion, which is applied in the propulsion of surface ships, aircrafts, rockets. So therefore, the impulse momentum principle will be applied in the jet propulsion, and the jet propulsion applications we can see such as in surface ships, aircrafts, rockets, etc. So another application is that momentum theory of propellers. So in propeller, here we can see the propeller, it converts the torque into the axial thrust. While it is converting the torque into axial thrust, it applies a force on a fluid and it changes the momentum of the fluid. And the fluid applies a force that due to that force, otherwise the propeller moves in forward direction and the liquid will be moving in the backward direction. There will be equal and opposite force as per Newton's law. Therefore, the momentum principle, the momentum principle also can be applied in the propellers. Propeller is a mechanism which uses a torque to convert into axial thrust. Okay, axial thrust is done by a propeller by changing the momentum of the fluid in which it is submerged. So when a propeller submerged in an undisturbed fluid rotates, its force applies a force on a fluid and pushes a fluid backwards while fluid is moving backward, and at the same time the device moves in forward direction. The reaction to this force on the fluid provides a forward force on the propeller itself, and this force is so called propeller thrust, which is used for propulsion. And another major application of the momentum principle is the force exerted by a flowing fluid and a pipe bend. So the force can be calculated by applying the impulse momentum equation on a pipe bend. The pipe bend may be in different cross section. It may be at 45 degrees. Okay, half of the section, remaining half of the section may be 90 degrees also. The pipe bend may be located like this, or it may be more than 90 degrees, about 135 degrees also. It can be drawn like this. It can be drawn vertical also. It can be 45 degrees also. But whatever the angle may be, the orientation of the pipe bend of the another section may be in the control value. So, but we can calculate the resultant forces Fx and Fy. These forces, so the Fx and Fy are the forces applied by a fluid mass on a pipe bend. But the negative of Fx and Fy will indicate the force applied by a pipe bend on the fluid mass. So these are the resultant forces we have to find out, Fx and Fy. So to the resultant force is F. So that also we have to calculate by applying the resultant forces. So in this case, if you consider a pipe bend, so you take a if you consider a pipe bend horizontally, so it's lying on a plane. It's lying on a plane. Whether the theta may vary from any angle to any angle, but its entire pipe surface is at a constant distance, at the same elevation from the ground. So that means it is like a paper kept on horizontal plane, lying on horizontal. So that's why whether this may be with a different angle, but Z elevation from the ground becomes Z1 and Z2 becomes 0. Both are at the same elevation. It is a constant height. So in this section, what we have to do is we have to consider section 1, and another in another section take this control value, a boundary at 2, and this is the control value where we have to find out the reaction forces and other unknown parameters. At section 1, the forces, what are the forces acting? Pressure force. Due to pressure, there will be pressure force P1, A1. So another, the velocity is horizontal direction only, V1, where fluid is moving into the V1. Okay, so in this direction, at section 2, what happens? Pressure force will be acting at theta. So as theta is 0 at initially, that is P1 A1, but at section 2, the pressure force will be acting in reverse direction. Therefore, P2 A2 cos theta. So because P2 A2 will be acting in reverse direction to the fluid flow. So the vertical pressure force is P2A2 sine theta. So then these are the pressure forces acting at section 2. So these are the pressure forces acting at section 2, pressure force acting at section 1, and the velocity at inlet is V1 and velocity at outlet is again this is moving with an angle V2 with an angle theta. So therefore horizontal component is V2 cos theta and vertical component becomes V2 sin theta. So now we are going to apply impulse momentum equation on a pipe bend on two sections, otherwise on a control volume, in order to calculate the reaction forces or on another parameters. Okay. So now consider the section 1 and 2 where velocity, pressure and area at section 1 and at section 2 also. Now let Fx and Fy be the components of the forces exerted by the flowing fluid on the bend in x and y directions respectively. Then the force exerted by the bend on the fluid in the directions of x and y will become negative Fx and Fy. So the other external forces acting on the control volume are pressure forces P1A1 and P2A2 at section 2. The momentum equation about x we have to apply in both the direction. Momentum equation about x and about y also. So if you apply a momentum equation about x direction, then what are the net forces acting on fluid mass in a control volume at section 1 and at section 2. So that we will take and we will apply in a impulse momentum equation. So the impulse momentum equation is F equals to ma. So where F is a net force acting. The net force is the forces acting on section 1 and section 2 includes. So the ma is the rate of change of momentum. This is nothing but dmv by dt. So that is nothing but mass per second and change of velocity. So now we have to apply the rate of change of momentum and the net force acting. The momentum equation or impulse moment equation can be applied about x direction on a pipe bend on a particular control volume. So then after applying it to different sections, then we will be getting the particular equation. At section 1, what is the force acting? Net force about x direction. So how many sections we have considered? Only 2 sections in a control volume. At section 1, what is the net force acting horizontally? Net pressure force is P1A1. Okay, about x direction moving along x towards rightward direction, therefore is positive, and the pressure force at section 2. So as it is theta, the pressure force will be acting in the downward direction. Therefore, P2A2 cos theta horizontal component becomes P2A2 cos theta. So backward, therefore negative minus P2A2 cos theta. And then the force exerted by the fluid, okay, is minus Fx. Okay, so that can be minus Fx. So now mass per second. This is the mass per second and change of velocity, product of mass and velocity, that will be a momentum, change in momentum, rate of change of momentum. So will be written like this. It can be written like this, mass per second. So this can be density times rate of flow. So density is kg per meter cube, density of water, and where discharge is in meter cube per second, rate of flow. So then you will get a mass in kgs per second. So then this is in kgs per second. Mass is kg per, then change in velocity. Velocity is initial velocity and final velocity. So final velocity along x direction, change in velocity will consider like this. Final velocity along x direction minus initial velocity in the same direction. So therefore, the rho q mass per second is nothing but rho q. So another one is final velocity at section 2. That is direction. Its direction is as according to the flow direction. It follows the flow direction. V2 is flow direction in forward direction. Therefore, So horizontal component is V2 cos theta, V2 cos theta positive. So therefore V2 cos theta, and at section 1 final velocity minus initial section 1, vertically there is no velocity. So only horizontal velocity is there, vertically there is no velocity. Therefore initial velocity, vertically there is no velocity, but horizontally there is a velocity. There is a difference between vertical velocity and horizontal velocity at section 1, because it's not resolving, but here there is no angle. At section 2 it resolves, there are two components, but section 1 only one component. Initially at section 1 horizontal v1x along x v1 is there, therefore v2 cos theta minus v1. So this is the rate of change of momentum, and the net force acting is p1a1 minus p2a2 cos theta minus fx is the net force acting on two sections about x direction, is equals to rate of change of momentum is rho q, density into density of liquid into liquid of particular liquid, and rate of flow of liquid into v2 cos theta minus v1 final velocity minus initial velocity. So from this, what is the force fx, the net resultant force along x, resultant force along x becomes rho q v1 minus v2 cos theta plus p1a1 minus p2a2 cos theta. So this is about x. Similarly, we have to calculate the net force acting in y direction at both the sections. In the y direction, if you apply the pressure force vertically, there is no vertical pressure force, therefore 0. And at section 2, pressure force at section 2 is also negative. So because it is coming downward, horizontal component, and P2A2 will be like this. Therefore this is P2A2 sin theta in vertically downward direction, therefore negative. Minus Y. So this is a force exerted by a bend on a liquid is minus Y. The force exerted by a liquid on the bend is fx. Okay, so this is positive. Another one is, so exerted pipe bend exerting the force on the liquid is negative. So minus fy, and rate of change of momentum, mass times mass per second into velocity, mass into velocity. So similarly, the mass per second can be written as density times discharge, okay, into final velocity minus initial velocity. Yeah, similarly, the final velocity rho q remains same. The final velocity it will be positive moving upward v2 sin theta, but initial velocity vertically there is no velocity, there is no pressure, therefore 0. Vertically there is no pressure force, sorry, velocity. So only horizontal velocity is there, so therefore 0. So from this the resultant force Fy, resultant force along y direction Fy can be written as rho q minus v2 sin theta minus p2a2 sin theta. So from this we can calculate the resultant force finally Fr about fx and fy is nothing but root of fx square plus fy square. We know the resultant force about x direction, about y direction, but about x and y, the resultant force finally fr is nothing but a root of fx square plus fy square, and we can find out this gives the magnitude of the force, and this gives the magnitude of the direction of the resultant force. Theta, tan theta equals to fy by fx. So if fy, fx is positive, you can write like this. If fy is positive, you can write like this. You can draw, and the resultant force will be in this direction. So if fx is positive, fy is negative, you can draw like this. This is minus fy. Then the resultant force will be in this direction. You can calculate the theta. So as per the direction you are getting, as per the sign you are getting for the resultant forces about f on y and x, we will find out the final resultant force direction. Okay. Now we will see one example. A 45 degree reducing bend is connected in a pipeline. its diameters are given at the inlet and outlet 600 mm and 300 mm respectively. Find the force exerted by the water on the bend. If intensity of pressure is 8.829 Newton per cm square and the rate of flow water is 600 lps. 600 lps. So you can draw the section like this. So initially its diameters are varying. Here 0.6 meter diameter, this is 0.3 meter diameter, and direction is 45 degrees. Is moving with 45 degrees. Theta is 45 degrees. Okay, here pressure force in reverse direction at section 1 in forward direction. So the various parameters given are theta, d1, and its discharge is given, q is given. Therefore, we can calculate the velocity v1, v2, and the pressure. One pressure p1 is given 8.8 to 9 Newton per cm square. So this is given, but p2 is unknown. P2 we have to calculate, and you have to calculate the force, resultant force Fr, and we have to calculate the theta. These are the unknown parameters from the given information. So to calculate these parameters, first of all we have to calculate P2. As P2 is missing, we have to calculate the P2. As the pipe bend is, even though it is 45 degrees inclined, the elevation from the base is at the same height. Therefore Z1 equals to Z2, you can cancel these two. The P2 is unknown, the remaining parameters are given. So therefore, in order to calculate P2, we need the Bernoulli's equation. The Bernoulli's equation states the total energy remains constant for a ideal fluid at any section. The total energy means pressure energy, kinetic energy, potential energy. These remains constant at section 1 and section 2 also. We assume that it's the ideal fluid. So that otherwise we have to add some of the losses for a real fluid. So from this, by assuming Bernoulli's equation, and we need the Bernoulli's equation in order to determine the pressure. Otherwise, there is no other alternate to calculate the pressure at section 2. So from this, we can calculate the P2 as the remaining parameters are given. Rho, density of water is 1000 and G is 9.81. P1 is provided 8.829 10 power 4. This is 10 power 4. Plus V1 square by 2G plus P2 by rho G plus this is V2 square by 2G. From this, the pressure at section 2 is 5.4 into 10 power 4 Newton per meter square or pascals. So this is P2. Once the P2 is known, we can apply the impulse momentum equation on both the sections at control volume 1. For the control volume at section 1 and section 2, we will apply the rate of the impulse momentum equation. Net force applied on a fluid mass is equals to rate of change of momentum. The first at section 1, pressure force is P1 A1. These values are provided, and P2 A2 cos theta. As at section 2, the fluid the pressure force acts in reverse direction, therefore minus P2 A2 cos theta. These values are given, and rho is 1000. We know Q is also provided. Q is the discharge through that pipe. Velocities V2 and V1 are given. As Q is known, we will be getting it from a continuity equation, and V2 cos theta minus V1. So from this expression, this expression is not constant, as we have to express, we have to write this, we have to obtain the expression for a given pipe bend, because pipe bend orientation may be about 45, about 90, about 135 at different angles. Its orientation will be different. Therefore, this equation will not be the constant for all the pipe bends. This equation will vary based on the orientation of theta. So, as theta is 45 degrees, then we can write the expression like this. From this, the resultant force Fx about x, force about x can be calculated as 19911.4 newtons. So this is a Fx. Similarly, the force about y direction is, again, by applying the momentum equation, we can calculate the pressure force at section 1 is 0 minus P2 A2 sin theta and minus Fy equals to rho Q V2 sin theta. So V2 sin theta is moving forward and the pressure force is downward. So therefore, now from this Fy can be remaining parameters are given, just you have to substitute these parameters and get Fy. Fy equals to minus 6322.2 newtons. So it is negative. Okay, negative sign means acting downward direction. Fy in downward direction. Therefore, the resultant force from Fx Fy is 20890.9 newtons. This is a resultant force for a given pipe bend for that particular direction. So here, this is the magnitude. How do you calculate its direction? Tan theta is equals to Fy by Fx. So from this, theta equals to tan inverse of Fy by Fx. If you substitute Fx values, we will get 17 degrees. So this is the 17 degrees. So we have drawn with 17 degrees Fx in the positive direction, Fy is negative, it's coming in the reverse direction. Resultant force will be in this direction with 17 degrees about x. Now another problem is given on a pipe bend, but here the difference is the diameter will be same. The diameter is same, but the angle is different. So angle 135 degrees. The pipe can be drawn like this, 135 degrees. It will be moving like this. So section 1, section 2. So say this is 90 degrees, and this will be 135 degrees. So here the various parameters are as per that. If you draw the diagram, where the pressure forces will become positive. So because it acts in reverse direction, therefore the pressure forces horizontally it becomes positive, moves forward direction, and the vertical pressure force becomes negative only. Comes downward, P2 A2 sin theta, and velocity is in the direction of flow, therefore V2 and V2 cos theta will be negative, V2 sin theta will be positive. This is a given information from this. Pressures are given as same, the pressures are same, and velocities are same. As the diameter discharge is constant, the velocities are same. So area and diameters also same at both the sections. Therefore, we'll write the expression net force about x on a given pipe diameter and for a given orientation of 135 degrees. It can be written like the P1A1 is positive. This is positive as the P1A1 is in the rightward direction. This is positive, and P2A2 this is also positive. It's moving in the forward direction. This is also positive. Minus Fx. This is a force exerted by a bend on a liquid. So minus Fx. This is a net force. This equals to net force. Net force is equals to rate of change of momentum, rho q, minus this is a mass, and the final velocity minus initial velocity. Final velocity is it's moving backward direction, therefore negative, minus v2 cos theta. So therefore negative. Final velocity minus initial velocity is positive only. So minus initial velocity. Final velocity minus initial velocity. From this Fx can be 48855.4 newtons. So if you substitute all the given parameters, the pressure, velocity, area, these are all provided. You need not to apply here Bernoulli's equation also to calculate unknown parameters. All parameters are given. Only thing is you have to calculate the force about x by applying the suitable expression. So by after drawing the diagram for a given orientation only, the resultant force about x can be derived. Similarly, along y direction, the y direction at section 1 there is no force, therefore 0. And pressure force is acting downward direction. Since it is downward direction, this P2A2 sin theta is negative. Minus Fy, this is the resultant force, is equals to rho q. The final velocity along y direction is V2 sin theta. V2 sin theta. So minus 0. So that is Fy is equals to here, from which we will calculate Fi is minus 20236.3 newtons, that is negative. Then resultant force becomes root of Fx square plus Fy square. From this, 52880.6 newtons. So then magnitude can be once magnitude is calculated, then direction can be calculated by the equation tan theta equals to F by Fx. Theta is 22 degrees, Fy is negative, so therefore it is drawn downward, and Fx is positive. Then the theta is 22 degrees. So these are some of the examples of pipe bend, numerical examples of pipe bend, and some of the applications of impulse momentum equation, and impulse momentum equation, how it can be useful for solving of numerical problems, complex problems in pipe bend, etc. we have seen. So with this, the impulse momentum equation, some of the examples are concluded. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.